Delegates, esteemed guests and dear participants, it is my honor and privilege to welcome you all to the technical session, the part of EFCS 2024 conference. I am Dr. Muhammad Mustafa TN, Assistant Professor and Head of Research and Postgraduate Department of Chemistry of MES Kaladi College, Manarkad, and I am delighted to chair the present session. In this session, we have three eminent personalities: Professor Tapas Kumar Maji from JNCSR, Dr. Aishwarya Bhaskar from Central Electrochemical Research Institute, Kozhikode, and Dr. Jadesh Kumar from ICET Tirupati. First of all, I would like to welcome Professor Tapas Kumar Maji, a luminary in chemical science. Professor Maji's pioneering contribution to molecular orbital frameworks and porous organic polymers have laid the foundation for numerous transformative applications in areas such as chemical separations, photocatalysis, and environmental sustainability. His innovative methodologies, particularly the covalent integration of light harvesting units with catalytic systems in molecular orbital frameworks, have redefined the potential of hybrid materials in the quest for clean solar fuel production. Professor Maji received the prestigious Shanti Swarupadgar Award in Chemical Science in 2019. He has also received several other recognitions, such as Bronze Medal of the Chemical Research Society of India and Material Research Society of India, the Sheikh Sakar Career Award Fellowship from JNCSR, and the Scopus Young Scientist Award and all. He is also a Fellow of the Royal Society of Chemistry, recognized as a leader in the field in 2019. With great anticipation and respect, I now invite Professor Maji to take the stage and begin with the exciting session. Sir, please.
Good afternoon. So at the outset, let me thank the organizer, particularly the chemistry department of Farook College, and being the pillar of this EFCS conference, Professor T. Pradeep, for the invitation to be here. Because actually I heard about this conference from my colleague, Professor Subi George. And when I got the invitation, I told him that, and he told, you must go there and encourage that young minds, particularly the younger generation, or which are the future of our country. So in this context, I would like to particularly thank Professor Pradeep. He is doing these things from the last 8 years. With this, so in the next 30 minutes, what I'm going to talk about, that little bit of work we are trying to understand that mimicking natures by the metal organic framework for solar fuel production. So, you know, I don't want to go much about that, why the CO2 reduction or CO2 storage and conversion is very, very important. But rather, I want to focus in this talk how our rational approach to understand the nature. Okay, nature is doing this billions of years, this taking CO2, converting food, and which are the all giving the sustainability of our life processes. And how in the molecular, as a chemist, how you can contribute in such case. Okay. So let me just, for the students, I introduced what is metal organic framework. So metal organic framework are a class of porous coordination crystalline polymers formed by the interconversion of metal or metal oxo cluster with the organic ligands having more than one coordination site. Okay. So you have a metal here and you have just kind of the linker. So all of you studied the coordination chemistry. Coordination chemistry is just like a metal complex. So when you have, let's say, metal and ethylene diamine, it forms the mononuclear complex. Instead of that, if you take the bridging ligand, you can get that kind of extended structure. Okay? So this is the metal which we call the node, because this term I will be using frequently. This is the node, and this cannot be the single metal. It can have the 2 metals, 3 metals, 8 metals, 12 metals. Not only that, it can be the chain, and this can be connected by such kind of the organic linker which different geometry, different conformational, different binding site, you can get the different type of structure which will be, let's say, one-dimensional, two-dimensional, three-dimensional, which have the different type of net topology. Okay, so all of you know, this is the basic coordination chemistry. If you have the silver has the coordination number 2. When you connect with the bridging ligand, it will form the one-dimensional chain. But instead of the, if you take that the cobalt or nickel, it is the generally coordination number is 6. So when you connect with this such kind of the linker, generally it forms the three-dimensional structure. Okay, so based on that concept of the crystal engineering, you can some sort of desired, or you can tune the structure based on the concept of the crystal engineering, tuning the metal ion geometry and the geometry of the bridging ligand. Okay, so this kind of material is the porous, highly crystallite, high surface area, and this has the high stability and the processability. So this is the such kind of SBU. So this yellow space are that you have the coordination space. That's the porosity, porous materials, okay? So porous materials are ubiquitous. You know zeolites, you know the activated carbon, you know the mesoporous silica, but this is the new type of material where you have the organic and inorganic building block which can form the extensive porosity, and where the properties can be coming from this your organic link and also from the metal ion. So which I am going to tell how we are designing to develop the catalysis based on this concept. Okay. So this, you have this kind of pores, these MOFs. Many groups in the world, they are working because they have the potential application for the storage of these molecules. Like you have the gas storage, it can be used for the separation, either separation size and shape of the pore, or the thermodynamic, where the isosteric heat of adsorption plays the critical role. Okay, so you can have the catalysis, optoelectronic properties, even that it can be the biological application like the bioimaging or the drug delivery application. You have this magnetism, so and so forth of this kind of material. So how do you synthesize this kind of material? So you have that kind of, you can take the diffusion control synthesis, you can have the solvothermal synthesis, microwave synthesis, mechanochemical synthesis, electrochemical synthesis, sonochemical synthesis, you can get the desired product. But this sometimes that certain condition or certain linker or certain organic functional group are not compatible in this synthetic condition. Okay. So then the term came that the post-synthetic modification of such material. So here the pre-synthetic approach have been used to construct a tailor-made MOF, but with a rather restricted functional group. You cannot have the large number of functional group you can put inside the MOF, because the condition, synthetic condition, sometimes it will decompose, sometimes you cannot connect that kind of material. So most functional groups are not compatible with the high pressure and temperature condition for the solvothermal reaction. Then come to the post-synthetic modification. Means you have a MOF, then after synthesis with the MOF, if you desire what functionality you want to introduce, you can post-synthetically modify. Okay? Means synthesis the MOF, then you modify post-synthetically. Okay? So this have the enormous. So you have the advantage of the greater control over the types and number of functional group that can be incorporated into the framework. Both metal and organic components can be functionalized without affecting the overall framework stability, and it is an excellent tool for preparing the topological identical. You can get the same material, topological identical, but the functionally diverse framework. So these methods are evolved from simple efforts to modifying the MOF to becoming a key synthetic tool for the range of emerging different type of application. Okay, so now you have a MOF. So now what you can do, you have a MOF, you can change the metal ion. This is called the metathesis. Either you can get the bicomponent, or you can completely replace the metal ion and you can get the completely desired product. Let's say you have a diamagnetic metal ion, you can replace with some sort of the paramagnetic metal ion. Okay? So then you can introduce the magnetism in the system. So it is called the metathesis. You can change the ligand, okay, completely, or you can diversify it. So if you have the, let's say, 5 different ligands, that is called the multivariate approach in synthesis of the MOF. So you can have the different functional group you can connect by organic synthesis, okay? So, or you can exchange the different guests and you can get the different properties by the post-synthetic modification of this MOF. So today let's come to that with the brief introduction, how by the molecular level tuning, you can get that make the artificial photosynthesis. So we know the natural photosynthesis is the process by which the sunlight is captured and converted into the energy of chemical bonds of organic molecules that are the building block of all living organisms, and also for the which supply the energy like gas, coal, and oil. So these fossil fuel are the product of the photosynthetic activity millions of years ago. Okay? So today, whatever the energy you are getting, because of this, the photosynthetic activity, which have the millions of years ago, it happened, and would provide us with most of the energy needed to power our technologies, heat our homes, produce the wide range of chemicals and materials that support everyday life. So this is the key for this energy and sustainable life process, the photosynthesis. Okay, so that artificial photosynthesis is that what? If you have the photocatalytic CO2 reduction into fuels and chemicals in water medium by harvesting the sunlight to reverse at the artificial photosynthesis. So now you can take the sunlight, whatever CO2 you can produce, and if you can convert, make the artificial plants, and then convert to fuels, so then you can have the whole cycles. And we have the plenty of the sun. If you 1 hour of sunlight, if you can fall in our plate, equivalent of all energy consumed by human in an entire year, if you can capture it, if you can convert it. Okay? So this just brief introductions, because I like these slides, how the nature has created this. So all of you know, it is not new. So this is that photosynthesis. It has the light phase reaction. You have this light phase reaction, what happened? It produced from the water, split water, you can get the oxygen, and then you can, from the NADP reductase, you can get the NADPH plus ATP synthesis and 2 proton. And in the dark phase reaction, CO2 plus NADPH plus 2 proton, using the ATP, you can get glucose and all these things. So now look at a little bit more detail. You have a chloroplast here, right? So inside the chloroplast, this part is called the stroma, and this is called the thylakoid. Okay? And when thylakoid membrane got stacked, it is called the grana. And inside that, this is your thylakoid membrane, where that photosynthesis takes place, and you have the lumen. So lumen is that like it is a macromolecular assembly where that you have the manganese cluster and oxidize to get the oxygen. Okay. So this is, let's say, look at the details of this membrane. So when you look at this membrane, this is that membrane. Okay. So you have the PS2, and here is the PS1. So in this PS2, the PS means the photosystem 2, all of you know. First it is that create the hole and electron, get oxidized, and H+, it's produced, and when oxygen produced simultaneously. So inside that is called the thylakoid membrane, that is called the lumen. And now what you see, because of this, that you have this PS1, this electron go to the PS1, and here it's produced from the NADPH to NADPH reductase. And this time you have a proton you get, and this protons is getting utilized here, and they create one kind of the proton gradient, and these proton gradients happen that ATP synthase and help to ATP synthesize from this in this membrane. Okay, so it looks like the Z scheme. So let's that you have the Z scheme kind of things. So you have the PS1, you have the PS2, this kind of things. So why the nature has to do such a complicated way? By the way, artificial photosynthesis is quantum efficiency is not good. It is maximum 2%. Okay? But why nature has to create this kind of process to get? One of the reasons is that you have the competitive reaction of the proton reduction. If this electron, it gets utilized by the reduce of the proton, then this electron transfer, it will not come here to quench the hole as PS1. So this to reduce the proton, that one of the reasons that nature has created such a complicated pathway to create the glucose. Okay. Interesting. So how we can do the chemical approach for the artificial synthesis. So this is the modular approach. As a chemist, we have the significant role to create such kind of simple way that whether to create some kind of take the sunlight, get the oxygen, split the water, get the oxygen, and take that CO2 and produce some kind of valuable product, either fuel or different type of chemicals. So this modular approach provides a way to meet the challenges based on the molecular excited state and the molecular assembly, and offers the advantage of investigating the individual components for light absorption and integrating them into the appropriate architectures toward the realization of artificial photosynthesis. Okay. So now when you have the semiconductor, sunlight, it creates electron and hole. So this electron can be reduced and the hole can be used for the oxidized. So if you want to do the CO2 reduction, if you look the reduction potential, so this is the challenge here. You have the 2 proton, 2 electron reduction. Either you can get the format or CO. But if you went that 6H or 6 proton, 6 electron reduction, you can get the methanol or 8 proton, 8 CH4. So you see, thermodynamically to reduce CH4 is easier compared to you have the format. But you see the number of electron involved. Here you have the 8 proton, 8 electron involved, means the kinetics of the electron transfer has to be fast. The density of the electron in the catalytic site should be more to get the higher order reduced product. Okay. So this light absorption, charge separation and migration, CO2 binding, redox reaction, and desorption of the product. So these are the cycle and many processes are involved. So this is why the selectivity and the efficiency is the key of this process. Okay. So there are many processes involved. So we have to try to understand that mechanism. When there is a 6 electron, 6 proton involvement, there are multiple intermediates are there. So these multiple intermediates, to understand how to stabilize, to get one particular product is the key. Okay. So this, our process will say that how it can be done. So MOFs offer the advantage of this. It has the porosity where your substrate can diffuse easily inside to the framework. You can tune all the structures. So the band gap of the material, you can easily tune either the pre-synthetic or the post-synthetic condition. It have the high crystallinity, so the defect you can modulate, and you can have the post-synthetic modification because it allow to modify the post-synthetic. So this is our approach. So now I am going to talk in only one MOF. So how it is that? So UIO 66, earlier people used to think MOFs are not stable. But this is the milestone research in the MOF chemistry. This is the University Oslo group. They first prepared UIO 66. This is the cluster. This is the cluster. I will go to the details. This is the cluster. So this is the zirconium 4+. 4+ is the oxophilic. Is the hard acid. And oxygen is the hard base. All of you know the SAB principle. It can forms the, you have this acid-base chemistry, very strong cluster. Then you isoreticular chemistry, you can synthesize by changing the ligand in the big way. So this is the way it can charge balance, it can 3-dimensional cluster. So look at how we can extend to our chemistry here. So we have taken one zirconium MOF. This is the MOF 808. It has the cluster. If you look at the cluster, there is a format. And you have the oxo, Me3O, Me3OH, and it is the 6. So now you connect with the tri-dentate ligand. This is this and forms the 3-dimensional structure, and 3-dimensional structure has that 2 different type of pore, either tetrahedral pore or adamantine pore. Okay. So now I want to look at, this is the very important part. You have a format here. This is the format, and this format group is here. So this format group I will be utilized for modification, post-synthetically modified my framework to introduce the molecular catalyst or the light harvesting moiety to look at the artificial photosynthesis approach. So you can create the defect. Either you can have the mesoporous MOF, which is the MOF 808, or the microporous MOF, which is also that you have the high surface area. So defect you can create by the synthetic condition, okay? And this MOF was reported by Professor Yagis from University of California. So how you can cluster modify it? So now you have a cluster, zirconium 4+. You can have the metal substitution. So zirconium 4+, there is no d electron. This is zirconium 4+, okay? So now if you take that one kind of redox active metal, you can substitute. Say let's say 1 or 2. Maximum you can do 1 or 2, not more than that. Because it is the octa coordinate. Your first row transition metal, iron, cobalt, it can only make like the 1 or 2. Or you can connect this oxo group, you can post-synthetically incorporate the metal ion, or this one, the format, you can substitute with R group, the different R group, okay? So this is that whole my next, whatever 20 minutes I am having, I am going to talk about all this part of this MOF, okay? So you have this now format group, zirconium MOF 808. So you can easily synthesize and monitor by the NMR. So now you have this format group, you can replace how many format group and the BTC from the NMR. So when you replace it after the post-synthetic modification, you can easily put the different kind of things and number of exchange. You can see you have the 4 format or 5 format or 1 format or no format. Okay. So then why I need such mob, the post-synthetic modification? If you look at, this is the one of the interesting paper published in the JACS. So from this, the linker, so you have a node, electron transfer is not possible because it does not absorb the visible light. So if you want to do the visible light catalysis, so because the sun provides the visible light range, right? The light, so you have to have the visible light absorption. So this is not possible because the node LUMO level is high, but only thing that cerium mob, the LUMO level is high. So we have one paper, EES, we have published, only the cerium mob, which I'm not going to talk because it's a different. So now you have to put some kind of the light harvesting moiety or tune to decrease the LUMO level. So if you have the LUMO level light harvesting, you can see the electron transfer, which is the higher. So it can be the lower. You have to increase this thing, okay? So this is our approach, how we can do. So this way, you can covalently grab. So this is the 2 molecular catalyst, either the light harvesting, our approach to put. So first what we have done, we have taken the same thing. Here is the format, COH group. Here you have the format. So what essentially you can do? You can take the bipyridine, you can connect. Simple coordination chemistry, all of you know coordination chemistry. So you have the COH. Now I have in the pore, there is a bipyridine ligand. So now what I did, I put the ruthenium bipyridyl Cl. So ruthenium bipyridyl, interesting, very classical inorganic coordination compound, all of you know, that is extensively used for different type of because of this high lifetime of the excited state lifetime, because it shows the 3 MLCT absorption. So now I put the 2 ruthenium here, or then I have the pre-bipyridine here. So then why either put that some kind of the molecular catalyst, rhenium or the manganese, you can put it here. So what I expect, because it does not absorb in the visible light, so the ruthenium bipyridyl, it will have the 3 MLCT absorption. So 3 MLCT, high excited state lifetime, it will go to the rhenium center or the manganese 1 center to do the catalysis, okay? So let's go how it is happening. So this is the whole process I've described. So to characterize it, that we do lot of characterization, I'm not going to bother you much. So this is the one, so that the mob structures remain intact here. So you have that octahedral crystal morphology, high resolution HRTM, it shows the 1.67 pore size. So when you post-synthetically modify it, automatically your surface area will decrease, should decrease, and it is decreasing from that 2424 to the 963, 28228. So now you see, after that when you incorporate, it was not emissive, the original mob, but when I put the ruthenium, it has become the emissive, and because of the MLCT absorption, okay? So quantum yield is very high. When I put the rhenium, further decrease the surface area, there is a rhenium MLCT band. So, fine. So what is the advantage I got? When I confine in the molecular container, this kind of the light harvesting moiety, you can see the lifetime of the ruthenium bipyridyl in the molecular state, it is the 185.5 nanosecond. But when you have zirconium mob ruthenium maybe, it's almost the double. So when you confine such kind of the molecular catalyst covalently grafting inside the pore, what it is? Because your thermal vibration, you are reducing thermal vibration. Okay, so the non-radiative pathway, it's decrease. Okay, so that's allow the radiative pathway, that's why the lifetime is more. So now, when you put the rhenium or the manganese, that the emission decreases, also that the lifetime is so suggesting there is a probability of electron transfer. This is the band structure, which is very important, that if you have the 0.63, it will connect this one. So now this is, you can, from the DFT, it is suggesting that the LUMO of this MLCT, from this, the bipyridine, it can go from the metal center to the bipyridine and goes to the rhenium, the bipyridine. So do the catalysis, fine. Next, we have done the catalysis and in the pure water medium. So we are doing the pure water medium. CO, it's produced, the 2 electron, it is the high selectivity, around 100%, it's produced. Turnover number is good and amount is good, but then we have done the many other kind of, take the different type of that you can say that your whole scavenger, either BNH, I'll tell you later what is the BNH, and it can produce. So that different control experiment we have done. So essentially that when you also in the presence of sunlight, it is also active, and it is, of course, it is the weather dependent. So I just put this vessel in the presence of our rooftop, and it is equally active, and it is, of course, the weather dependent. So we try to understand the details. What is happening here? That is very, very important. Then only you can go to the next level. So it is happening, the reductive quenching. There is a term, oxidative quenching, reductive quenching, all of you know probably when you studied this MSc, particularly the organometallics. So this reductive quenching happen means that when electron and hole create, first the hole is get quenched, electron will be available. So then we have the transient photocurrent we have done. It shows the in case of the ruthenium iridium, suggested the electron transfer, means the electrons charge separation is high in this case, also further supported from the impedance measurement. Okay. Then we try to understand that what is the mechanism of this. So mechanism you can understand by the in situ IR measurement, because this is very, very sensitive technique. So I am putting the light, I am getting the CO2 environment, I have the catalyst, then I am monitoring what is happening. So first, it is my background, that first, before the CO2, it is the background. Now you see, according to the irradiation time, I am seeing some sort of the band. 1314, it is the bicarbonate, H2O plus CO2, bicarbonate, it forms. Now, it is the 2 electron. First, it is go to the COH, CO2 plus electron plus H plus, it will go to the COOH. You can see my COH band here. It is increasing the intestine. And the next step, water, it will go out and it will form the CO. So now you are getting the CO, this 2060 peak. So I can real time, I can monitor what is happening in the reaction. So then further we have performed the DFT calculation to try to understand really happening. So first, bipyridine gets the electron, then it is through the oxidative quenching, oxidative addition, CO2 binds and CO2 to COH, then H2 and CO, and it is released there. And it is the free energy suggested, it is the thermodynamically feasible process. Because all the exergonic process, I have the negative free energy change. Okay, how much time I am having? 5 minutes, thank you. So, next, okay, fine. Then we have performed that another half reaction. So half reaction, we are getting the oxygen, okay? This is the oxygen evolving. So what I am taking, I have taken CO2, sunlight, my catalyst. One side I am getting the solar fuel, another time I am getting the things. So this we have mimicked that so it does very much different type of media. It explores the researcher mimicking the photosynthesis, which can convert CO2 to the solar fuel. Okay. So now you can argue it, okay, this is the ruthenium, it is the little bit of rare material. So can you tell something different way you can mimic this process? So then what we came across, so if you look at this process particularly, so now in the same MOF, what I have taken, I have confined the donor and acceptor complex, okay? So what is this? So if you have the electron-rich donor, if you have the electron-deficient acceptor, and if you confine cofacially, it forms the charge transfer complex, okay? If the association constant is very, very high. So I am using my pore to confine this, okay? Just two simple building block. What we have taken the pyrene and methyl valigine, okay? So now when this charge transfer form, so this donor acceptor, so this will channel either this electron it will take from here and it can go to the methyl valigine, and now it will go to the node, which is zirconium cluster, and it will be when the CT complex forms, this complex has the low energy band which comes under the visible light. Okay, so this process, so this is just whole things. So I have covalently first linked this one. Format I have replaced, then I have connected this methyl valigine. So now you have the donor acceptor, this kind of arrangement inside the pore. Okay, this color change. So I have taken the mesoporous MOF, which is the defect, because I can easily such kind of molecule in the put. So there you can see when further decrease the surface area, pore volume decreases here, and you have this HRTM showing the mesoporosity, okay, high resolution. So now if you look at the color, so when I have the pyrene butyric acid, so this has this cyan emission because it forms the excimer inside the MOF. So when I put the methyl valigine, that donor acceptor charge transfer complex form, and I get the CT band, and there is a emission vanishes. Okay, when the charge separation, that emission will be not there. So now you can see from the lifetime decreases from this, you have this hexamer, and when the methyl halogen, it is the 1.2 nanosecond. There is a charge separated state. In the light, normal light, there is a charge separated state. But when you have synthesis this molecule in the dark, there is no charge separation. We have done it, okay? So this is the feasibility of the electron transfer, that you have the LUMO. HOMO is in the pyrene butyric acid, LUMO in the methyl halogen, and it can go to the cluster easily. So I have done the Morse-Schottky analysis to understand how it is happening and the band structure. I'm not going to much time, my time is not. So I have used this kind of sacrificial agent. This is very, very important. This is 1-benzyl, 1,4-dinitronicotinamide. So what is the reduction potential is very high. So that means that the oxidize, it forms the dimer state. And this oxidation potential only 0.29 volt. So it can quench whole efficiently. And now we are getting, instead of the CO, we are getting 8 electron, 8 proton reduction to get the methane. Okay? We are getting now the methane. So 8 electron, 8 proton reduction. So 7.3 millimole per gram, turnover number is 28, and activity is also quite high. So then we try to understand it in that EPR. So this is the light induced that you can do the EPR, in situ EPR, okay? So now when you are the methyl halogen, zirconium is the 0, 4 plus, there is no d electron, but it is the electron transfer is happening, and you are getting the zirconium 3 plus. G equals to 2.01, as well as the CT also increases. That it is showing that is the indeed electron transfer is happening, okay? So then further we try to do the transient absorption, okay? So transient absorption, what we are getting? So this is the pyrene cation radical, and is the methyl halogen radical. This is the excited state absorption band. So when the decay we have analysis at the 450, so this you can see there is a different decay. So this does mean the distinct decay time, there is no energy loss between the two. There is no electron hole that it is again, they are just electing hole, it is coming together. It is not. The distinct, it is showing there is some kind of decay time, and this whole process that electrons can come here and this donor to the acceptor to the methyl halogen. Okay. So then again we have tracked this whole process. Little bit of problem. Yeah. Again in situ we have done. So it is the 8 electron, 8 proton reduction. So you have the CO2 to CO2 dot, CO2 COH, then CHO, CH2H, CH3OH, CH4. So this, all the intermediate, we can track here, all these things, okay? So now you know the CH staging frequency, it comes around 3000. So all the CH4, so you can see the CO, which is that, but CO intensity is less because CO immediately it is converting to the another product, okay? CHO, and eventually, that's why the concentration is less. So then we have done the free energy calculation to further understand this process. So this is the whole concept how we have done it. Okay. So next, just 2 minutes, I'll take it. So this is the, okay, now, is it possible to now put some sort of the metal ion here? That cluster, zirconium cluster. So in the pre-synthetic. So now what we did, we put one of the metal ion iron, okay, here. Okay. So earlier I told that format exchange, but this is very difficult because it is the 8 coordinate and iron first it is the 6 coordinate. So what we have done, this is the whole process. So then after that, when we have done the ruthenium, again put here. So what we see here, instead of that 12 electron reduction process, we are getting the ethanol here, okay? So 12 electron, because this is the site, and there is a CC bond formation here because of the asymmetry in the unit. So from this, you can get the liquid product. From this, you have the 8 to 12 electron process. So then you have, again, instead of the ruthenium, can you take the iridium here? So when the iridium, again the basic coordination chemistry, iridium 3 plus, that because of this, that your delta 0 is very, very high because it is the 3 plus charge compared to the ruthenium. And you have the, this is called the PPY ligand, that this ligand which is connecting, it is that it is the strong sigma donor. When you have the strong sigma donor, that again the delta 0 will be better. Classical coordination chemistry. So now we put the iridium here and iridium. Then when the iridium to cobalt, we see there is acetic acid. We are getting the another 8 electron reduction process, acetic acid. But when you put the cobalt, it can go to the CO. So you can tune the electron transfer pathway here. Okay. So we do a lot of work, other system in the, this is not only the MOP, to understand. Here, sometimes the neighboring group can participate, okay, to stabilize the intermediate. So that is the very interesting, we are trying to understand if you can stabilize the CO by some sort of the neighboring group participation, because CO is the electron deficient, that time you can go to the higher order product, okay? So this is the summary, what I wanted to tell you, that is the very, very basic coordination chemistry I have applied to develop the catalysis. So it is the molecular level engineering inside the port, where you can see the light harvesting moiety as well as the catalyst. So to show the electron transfer process here. So this is the, from this here to ruthenium to rhenium. So then we have just simple organic molecules you can put, donor acceptor. So show the donor accept electron transfer to here. And if you can do the electron transfer change from here, okay? Either you can directly note, or there's some additional single metal cobalt, you can go to either acetic acid or CO, or you can get the CH3OH if you can cluster modification with the iron, okay? So also we do a lot of work with the, not only the CO2 reduction, you can get the HER also. So you can confine some semiconductor like the cadmium sulfide, you can get the post, but same MOP, you can get this kind of product, okay? So this is the conclusion that, first of all, Professor Rao, so because of him today, whatever I can do the little bit of research, his generous support, choosing me single-handedly to put the JNCSR, constant support, still he's supporting coming, so the great inspiration for us. So this is that. So we have that maximum work. I showed the Sanchita's work. She is now doing postdoc, and the Sneha's work is the iron cluster. Sneha Raj, she is the alumni from this college, Farook College, and she is doing really exceptional work. That Sneha, she is here, Sneha here, and I think Sneha is not there. Okay, Sneha in this picture is not. So thank you very much for providing there such kind of student, and the financial support from the JNCSR and also different funding agency, and we SSL research facility, and we have the supercomputing as the Paramukti facility in our campus. And we do a lot of that, I did not talk about much, to understand the coordination geometry. So we go to the DAISY beam line, we do the ZENS and XF study, because there is a, to understand what is happening, the coordination number is changing or not, we do a lot of. And we have the collaborator for Bark, this who does the TM measurement, Jyotisman also from TIFR, Professor Ishwar, and theoretical support I get from this, my colleague, Professor Poti, Professor Wagmade, Professor Bala. And thank you very much for your attention. I'll be happy to take that answer. Any question you want to have.
Thank you very much, sir. Now it is a time for interactive session. I request all participants to engage actively, please.
Very nice work, Tapas. Very impressive. About your lifetime, that the lifetime has doubled when you put it inside the MOF. Did you also look at the quantum efficiency, luminescence quantum efficiency? Because you are showing the average lifetime, it has at least 3 components. And somehow, if you reduce the first component, it might artificially look very high, but your quantum efficiency might be very low. So did you look at the
quantum efficiency? We got around 14%.
And when it is outside?
Outside, it is just maybe 3%. Quantum efficiency significantly enhanced.
That's
so
very
we know. So that's why we are telling, because we are putting the molecular level confining. So we are just it stopped the thermal vibration. That's why that your different non-radiating pathway decrease, lifetime increase. But that may not be correct also. So
is it thermal or Brownian motion basically you are stopping? But they are still moving.
It will be less compared to thermal motion, right?
Yes.
So but recent papers are coming. There is a vibrational level coupling. Some calculation it is there people are telling. The vibration level coupling. That also increase the lifetime when you confine such system in that. But we have not, because, but one of the reasons that we try to understand that this is the way. But iridium case is again very, very high, because iridium case.
Thank you.
Very nice talk. Thank you very much. In your cluster system, you have 6 of these clusters. And inside these, there is a donor acceptor or some kind of molecular system which is undergoing transition. So that transition is eventually producing an electron. It goes to the outside the cluster surface, which is doing catalysis. And it's doing a whole series of catalysis, this 8 proton transfer. Now, it is also possible that many of these species will be doing many other reactions. And so all these are, the complexity is increasing. So my question is, that one chemistry, one electron is doing something at one cluster surface. Next chemistry, is it happening on the same cluster surface or goes to the next one? In this process, all these 6 clusters are involved or only a few are involved? Is it possible to selectively do a series of processes at one site? Is it possible to investigate?
So this is a very intriguing question actually. So, because when we excite the electron, so it is going to the particular cluster. But eventually, in the framework, it is not the single cluster. We have the many. And many light harvesting systems are there. We are exciting simultaneously. So, in my opinion, in the surface or in the diffusion, many clusters involves together for the CO2 reduction. That whatever we understand this process. Because if it is not there, so probably we should not see higher turnover number. Okay? So we are seeing the higher turnover number. Means there are many sites are involved. Whatever we try to understand, this question we also ask. But the problem is that when you try to look at the single cluster diffusion, that it will be no longer the heterogeneous system. It will be like a homogeneous system. Okay? So that will be kind of the single site catalysis. Means the single atom catalysis. So single atom catalysis has the maximum atom utilization, whole atoms are involved. But in my 6 cluster, maybe 2 clusters are involved during the process of this, where that we are seeing the CC reduction, CC bond coupling, where the 2 metals are involved.
Beautiful. So why is that this electron that you have generated is not destroying your framework? So this autophagy that he was talking about, why is that it is so selective to CO2 or all the series of transient
that bonds are not breaking, why?
No, why this cluster is stable?
Okay.
And it is only selective to CO2.
So that is the very beautiful questions that you have. That's why I was taking the zirconium 4+. This is highly oxophilic. 4+ is the basic SAP principle, hard acid base. So it connects with the oxygen very strongly. That's why even in the high different pH, so this kind of MOPs are only stable. That's why we can allow to do the catalysis in this. So that means when it is going to that state, so whatever CO2 in the CO2 medium or the different zirconium, it can take up the electron very easily. Because the so strong bond form, so it does not break that other things through this.
So when is it possible that your reaction bottle, I can put it under my kitchen and produce methane? When is it possible?
So that is we are trying. So we are trying to a jar where we are trying to take that, it is under process, but we are to put that some kind of jar where we are taking the atmospheric CO2. So that is the next level. Maybe next time when I will come, I will show that result.
Okay, thank you very much, sir. So, on behalf of EFCS organizing committee, to express our deep sense of gratitude, we would like to present a small token of love and appreciation to you, sir. Sir, please.